In this lesson, we'll focus on linear models, how to interpret the rate, the starting value, and when a linear model does or does not make sense. Why are linear models tricky on the SAT? Because the math itself is usually not difficult at all. In many problems, you can quickly find the equation, identify the slope, and read the intercept. But the SAT is not testing whether you can do those steps. What really matters is whether you understand what the model means in the situation. A linear model tells a story about how one quantity changes as another quantity increases. The slope is not just a number, it represents a rate, and that rate only makes sense when you pay attention to the units. The intercept can also be misleading. It shows the value when x equals 0, but in some situations, x equals 0 is not realistic at all. So even a correctly written equation can be misunderstood. Another common issue is prediction. A linear model may work well within the data range, but it can become unreliable if you use it far outside that range. On the SAT, many mistakes happen not because the math is wrong, but because the situation was misunderstood. That's why interpreting the model correctly is more important than simply calculating an answer. So, what is a linear model? A linear model is a model that describes how one quantity changes in relation to another at a constant rate. First, that phrase, constant rate, is the key idea. It means that when x increases by the same amount each time, y changes by the same amount each time. The change is steady and predictable. Second, that's why linear models are often shown as a straight line. A straight line visually represents the idea of the same change happening again and again. Third, remember that it's a model. Models simplify reality. That means a linear model is useful for making predictions, but usually only within a reasonable range where the constant rate assumption still makes sense. In the next slide, we'll focus on the most tested part, the rate or slope, what the model changes by for every increase of 1 in x. Now let's focus on rate, also called the slope. The slope tells you how much y changes when x increases by 1. First, remember that slope is a rate of change, so you should always think about the units. A slope of 1 could mean $1 per hour, 1 point per test, or 1 mile per minute. The number only makes sense with the context. Next, the sign matters. With a positive slope, y increases as x increases. With a negative slope, y decreases as x increases. And with a slope of 0, y stays the same, no change at all. Here's the SAT habit that prevents mistakes. Say the slope as a sentence. On this graph, the run is +1 and the rise is +1, so we can say, for every +1 in x, y changes by +1. If you can say that clearly, you're interpreting the linear model correctly. Next is the intercept, also called the initial value. The intercept is the value of y when x equals 0. On a graph, the intercept is the point where the line crosses the y-axis. In context, it represents the starting amount, before time passes, before hours are worked, or before anything changes. This is a common SAT trap. The intercept is only meaningful if x equals 0 is a realistic situation. If the model starts at a different time, or if x equals 0 is outside the real range, then the intercept might be just a mathematical feature, not a real-world starting value. So whenever you see an intercept, ask two questions. What does it mean in words, and does x equals 0 make sense for this situation? Now let's talk about using a linear model to make predictions. There are two cases, interpolation and extrapolation. Interpolation means you predict inside the data range, between values you already know. This is usually safer because the model is being used where the data actually supports it. Extrapolation means you predict outside the data range, beyond the largest or smallest x values you've observed. This is much riskier because the pattern could change, even if the line looks reasonable. Here's the SAT habit. Before you compute anything, ask one quick question. Is the x value you're plugging in inside the data range or outside? If it's inside, interpolation is often reasonable. If it's outside, treat it with caution, and be ready for a model limitation type question. Now let's talk about model limitations. A linear model is useful because it's simple, but it also makes a big assumption. The rate of change stays constant. In real life, that assumption often breaks. The relationship can speed up, slow down, level off, or change direction. That's why predictions are usually most reasonable within the data range and under the same conditions the data came from. When you go too far outside that range, you might still be able to calculate a value, but the result may not be realistic. On the SAT, limitation questions often come from the context, not the math. For example, Money can't drop below zero, a stadium has a maximum capacity, a discount can't keep increasing forever, and a machine can't run at the same rate indefinitely. Here's the SAT habit. Before trusting a linear model, ask, is a constant rate reasonable here, and is this input value within a realistic range? If the problem includes wording like, at first, eventually, maximum, or cannot exceed, that's a signal that a simple linear model may not apply for all values. Before we start the practice problems, here's a quick checklist for reading any linear model on the SAT. First, identify the slope. Slope is the rate of change. Say it in words. For every increase of 1 in x, y changes by the slope. And always connect it to the units in the problem, like dollars per hour or points per test. Second, identify the intercept. The intercept is the value of y when x equals 0. In context, it's often the starting value, but only if x equals 0 is realistic for that situation. Third, if the question asks for a prediction, check the range. If the x value is inside the data range, that's interpolation. If it's outside the range, that's extrapolation, which is riskier. Finally, think about limitations. A linear model assumes a constant rate, so ask, is a constant rate reasonable here? If you follow these steps, linear model questions become much easier and much safer. Here's your beginner practice. A plant starts at 10 centimeters and grows by 2 centimeters each day. What will the height be after 7 days? You have 60 seconds to think, no need to pause. Let's follow the slide format. Answer, why, and key idea. Answer. The linear model is h equals 2d plus 10, and after 7 days the height is 24 centimeters. Why? Start with the intercept. The plus 10 is the starting height, because when d equals 0, day 0, the plant is already 10 centimeters tall. Next, the slope is 2. That means the height increases by 2 centimeters every 1 day. On the SAT, always say the units out loud, 2 centimeters per day. That prevents common mistakes, like mixing up days and centimeters. Now compute. Plug in d equals 7. 2 times 7 is 14. Add the starting 10, and you get 24. So h equals 24 centimeters after 7 days. Quick sanity checks. At day 1, the model gives 12. At day 2, it gives 14. That pattern shows the constant rate. On the graph, the line starts at 10 on the y-axis, then rises by 2 for every step of 1 to the right. After 7 steps, you've added 14 total to the start, landing at 24, so the result is reasonable. Key idea. Say the model as a sentence. Start at 10, then add 2 centimeters each day. If your sentence matches the story, your equation is correct. If something looks off, recheck the slope and the intercept. Here's your intermediate practice. Use the table to estimate the cost for 2.5 days, then decide whether that prediction is interpolation or extrapolation. You have 60 seconds to think, no need to pause. Here's the answer and the reasoning. First, notice the pattern in the table. The costs are $18, $26, $34, and $42 for days 1 through 4. Each time the number of days increases by 1, the cost increases by 8. So the rate of change, the slope, is plus $8 per day. Next, we build a linear model in the form, cost equals 8 times days, plus a starting value. We can find that starting value using any data point. Use day 1. When d equals 1, the cost is 18. So 18 equals 8 times 1 plus b. That means b equals 10. Now we have the model. Cost equals 8d plus 10. The question asks for 2.5 days, so substitute d equals 2.5. 8 times 2.5 is 20, and 20 plus 10 is $30. Finally, classify it. 2.5 is between 1 and 4 days, so it is inside the data range. That makes this interpolation, and this kind of estimate is reasonable. Advanced practice. Don't just read the graph. Write equations for both shops. Cost A, H, equals 12 plus 3H, and cost B, H, equals 18 plus 2H. Solve the break-even point algebraically, then answer the real question. When is shop B $10 cheaper? 2 minutes. Show your work. Alright, let's go through the full solution step by step, and make sure the algebra matches what the graph is telling us. First, we write the equations for both shops. Let H be the number of hours. For shop A, you pay a $12 start fee, and then $3 per hour. So the model is, cost A, H, equals 12 plus 3H. For shop B, you pay an $18 start fee, and then $2 per hour. So the model is, cost B, H, equals 18 plus 2H. Now, part 2 is the break-even point. Break-even means the two costs are equal, it's the intersection of the two lines, so we set the equations equal and solve. 12 plus 3H equals 18 plus 2H. Subtract 2H from both sides, so we keep the H terms together, that gives 12 plus H equals 18. Now subtract 12, H equals 6. So the break-even time is 6 hours. But we also want the cost at that point, because a break-even point is really a pair, time and cost. So plug H equals 6 into either equation. For shop A, 12 plus 3 times 6. 3 times 6 is 18, and 12 plus 18 is $30. So the break-even point is 6 hours and $30. And if you look at the graph, that's exactly where the two lines meet. Now, part 3 is the key twist. After the break-even point, when is shop B $10 cheaper than shop A? This is where we stop thinking, intersection, and start thinking, difference. If shop B is $10 cheaper, that means shop A costs $10 more. So we can write, cost A, H, minus cost B, H, equals 10. Now substitute the formulas. 12 plus 3H, minus 18 plus 2H, equals 10. Let's simplify carefully. Distribute the minus sign. 12 plus 3H minus 18 minus 2H equals 10. Now combine like terms. For the H terms, 3H minus 2H is H. For the constants, 12 minus 18 is negative 6. So the left side becomes, H minus 6 equals 10. Add 6 to both sides, H equals 16. So at 16 hours, shop B is exactly $10 cheaper than shop A. Let's verify, because checking keeps you from making sign mistakes on the SAT. At H equals 16, shop A, 12 plus 3 times 16. 3 times 16 is 48, and 12 plus 48 is $60. Shop B, 18 plus 2 times 16. 2 times 16 is 32, and 18 plus 32 is $50. So A is 60 and B is 50, the difference is $10. Verified. Now, part 4. Why does shop B eventually become cheaper even though it starts higher? This is the big linear model idea, intercept versus slope. The intercept is the start fee. Shop B starts higher because 18 is greater than 12, so at 0 hours, B begins above A but the slope is the rate per hour. Shop A increases by $3 per hour, while shop B increases by $2 per hour. That means every hour, shop A is rising $1 faster than shop B, so after the break-even point, the gap keeps growing by $1 per hour, and that's exactly why shop B becomes cheaper and stays cheaper. So the SAT takeaway is: write the equations, find the intersection for break-even, and when the question asks about how much cheaper, set up a difference equation. And always interpret it. The option with the smaller slope eventually wins for large H, even if it starts higher. Let's wrap up the key takeaways for linear models. A linear model describes a relationship with a constant rate of change. That's why the graph is a straight line. The slope tells you how much y changes when x goes up by 1, and the intercept is the starting value when x is 0. On the SAT, many word problems fit the pattern. Cost equals a start fee plus a rate times time. When you make predictions, remember the difference between interpolation and extrapolation. Interpolation stays inside the data range and is usually reasonable, but extrapolation goes beyond the data and can be much less reliable. And when you compare two linear models, the intersection is the break-even point, the moment both choices cost the same. After that, the option with the smaller slope tends to win because it grows more slowly. So if you can write the equations, interpret slope and intercept, and use intersections to compare, you're in great shape for SAT linear model questions. Thanks for watching, and I'll see you in the next lesson.